Today we're going to start talking about Newton's laws. The first law is about inertia. Aristotle was the first person who talked about nature of motion, and his observations were simple. If you have an object, he noticed that as long as you push on it, it moves. As long as you leave it, it stops moving. And that was his principle. He said for something to be moving, a force or something needs to be pushing on it or pulling on it. And of course, that it is not the picture that we have these days, although that was coming from observation. Galileo was the next one. Galileo was thinking this way. It says that if something is going downhill like this, it picks up speed, it goes faster and faster. If something is going uphill like this, slows down. So he thought if the road is level or the surface is level, something that's moving should move on forever. That was his understanding. But the way Newton thought about it was a bit different. Newton realized that there is something that stops the objects when you push on them and they stop, because he noticed that when you push on them, they don't stop immediately after you stop pushing on them. It goes a distance and then stops. He realized there's something holding it back. And if you make it more slick, so it's more smooth, it will go farther to stop. It still stops, but it goes much farther. Therefore, he thought that, okay, if you could make it completely smooth, it will go forever. That's why he devised his first law, said that if there's no force acting on an object, or net force on an object is zero, if it is moving, it continues moving forever on a straight line at constant speed. If it's not moving, like this one right now, it will stay at rest. And that is the Newton's first law. Where do you see Newton's first law showing itself in your everyday life? But I want to mention a couple of things. For example, why do we have seat belts in our cars?
So we don't fly across the dashboard.
That's right. So can you put it in that context? So what happens if we don't have seat belt?
We keep moving.
Yeah, we stay in motion.
Yeah. If you don't have a seat belt and the car suddenly hits something and stops so suddenly, then your body will keep on moving. And then because the car is stopped, you will hit the steering wheel if you're a driver or the dashboard. So that is one of the examples that the Newton's first law is at work, and we design things to prevent that. Can you think of something else? Have you seen the washing machines? How do they take most of the water out of the clothes when you wash them?
By spinning,
Yes.
the water goes out.
Yes, if you spin them, the water goes out. Why does the water go out?
Centripetal stuff.
Yeah, centripetal force,
Acceleration. Because
So-
the velocity would be tangential. I don't know.
Yes, if something is spinning, suppose there's a piece of clothing here and there's some water on it, and it is moving this way at one moment, then you change the direction of the cloth, but the water needs to go straight. And you change the direction of the clothing, the water keeps going straight and gets away from the clothes. Let's say you're at the beach, your clothes is wet, you want to dry it, what do? You can do that also, right? What do? You change the direction of your clothes, the water tends to go straight and gets away from the clothes. Or when your hand is wet and you want to take some of the water away and you don't have towels, what do? You do this, right? What do? You set everything in motion and then suddenly stop your hand. And the water keeps going and goes away from your hand. There are lots of these kind of examples that you can see, and these are all because of Newton's first law. That says if the net force acting on something is zero, then that object, if it is moving, it will continue moving on a straight line. If it is not moving, it will stay at rest. So that's Newton's first law. Newton's second law talks about the relationship between net force and acceleration. So in order to get into that, we need to talk about the force. Force as vector. You know that force has magnitude and direction, right? So because it has magnitude and direction, we study forces as vectors. This is an example of force vector. We draw a vector for that. There's a point where it applies and it has some direction. So force is a vector. But there are different forces that we talk about. In this course, we talk about these forces. One of the forces that is always present is the force between any object and the earth. Earth attracts every object downward, and we call it the weight. Weight of objects. So if you have a ball or something, there's a force applied to it. We call it W. And no matter what is happening with that object, this force is always present. And we call it weight. So weight of the object, and is denoted by W, and it is always downward. So this is one of the forces. So these are the forces we have in this course. Another force that's sometimes present is when an object is in contact with something else, a surface. For example, if I'm pushing on the surface of this board, the surface pushes back. If I'm pushing on the surface of the table pushes back with the same force. And that force is perpendicular to the surface. So if this is a surface, you push on it this way, and it pushes back. This force is called normal force because it is perpendicular to the surface. It's denoted by N. And of course, we can put arrows on these. Each one has a direction. The direction of the weight is always downward. The direction of normal force is always perpendicular to the surface. So whichever direction the surface is perpendicular to it. For example, if you have a wall that's vertical, the normal force of the wall is horizontal. If you have a surface like that, the normal from the surface is like this. And it's always from the surface toward the object that is in contact with it. For example, if you have an object on this surface, this is the normal force of the wall on the object. And also sometimes we have some rope or string connected to something. If you have a rope connected to something, we have that rope, for example, let's say it's a box and it's connected a rope in it. This rope applies a tension force denoted by T. It's always from the object toward the rope. So tension force. This is perpendicular to the surface, away from the surface. This is always downward. This is from object toward the rope, in the direction of the rope connecting the object. For example, if the rope is like that, the tension force is like this. And also there are two kinds of friction forces. We have kinetic friction and we have static friction. We're going to talk about friction in more details later, but here we just named it. Kinetic friction, which we call Fk, and static friction. Static friction force, Fs. So we use lowercase f for these friction forces, with subscript k for kinetic, subscript s for static. Kinetic friction is when there are two objects that are moving against each other. Like if the box is sliding on a surface. And static friction is when they're not moving against each other, but there is friction. For example, if you see this box in here, and you tilt this, it's not moving. What is keeping it there? The friction. But they are not moving against each other. So that's a static friction. In this chapter, we only talk about these, and also we have a couple more. Sometimes if there's a spring, there's force of a spring. If you have a spring connected to a wall, and on the other side, there's an equilibrium. The relaxed length of its spring, when you don't leave it, it doesn't move from there. But if you move it from that position this way, you have to push this way, and the spring pushes back toward the equilibrium. If you compress it, it also pushes back toward the equilibrium. So if you move it this way, the force is this way. If you move this way, let's say if this is x, that is a spring. If you push it this way, the force of the spring is that way. So the force of a spring is always toward the equilibrium point. That's why they usually say Fs is equal to negative kx. But with our notation, because we use the vector's name without arrow, we use it for magnitude. But here, it is a little bit confusing because a magnitude can be negative, right? So if you want to write it correctly, you should say this is Fsx to become component of x component of the force is equal to negative k times x. If x is positive, the x component of the force is negative and vice versa. And this is for when the equilibrium is at x equal to 0. And this k is called the spring constant. It shows how strong the spring is. And all of these forces have a certain unit. The unit of force in honor of Newton is called Newton. It's a Newton. All right, so now when we talk about forces, we usually talk about these forces. There is no force, there is a drag force, and something moves through the fluid. Like when a leaf is falling through the air, it just comes at constant speed. There's a drag force that keeps it from accelerating. And also, if you're moving in a fast car, you put your hand outside, you feel the drag of the air. Or if you move through the air, you feel the drag force. Sorry, did I say air? If you move through water, you feel the drag force in the water. So any fluid, when something's moving through it, there's a force, it's like a friction force, we call it drag force. And there's also a thrust force of the jet engines. The jet engines push gas in one direction, they go in the other direction. The gas pushes on the engine on the other way. But we don't talk about those forces that much unless, specific situation. So we leave it for when it is needed. So other than those, whenever we talk about forces, these are real forces that we talk about. There's nothing else. Normal is when you have a surface. Tension is when you have a rope or a string connected to the object. And friction is also when you have a surface and an object tends to move or moves against the surface. And spring force if you have a spring. So once, if you don't have these things, then you don't have that force. But the force of gravity, weight is always there, no matter what, if the object is massive. But there are some forces that people talk about, for example, centripetal force. We don't have such a force as real force. When we talk about what are the forces acting on something, it should be one of these forces. There's no centripetal force, there's centrifugal force. Those are fictitious forces. They don't exist. They are felt in a non-inertial frame of reference. These are not real forces. Okay, so these are the catalog of forces that we use only. Nothing else. In this course, you have either weight, normal force, tension force, friction force, or spring force. That's all. For example, people think that when you're moving in your car, suddenly your car turns, you feel that you're being pushed away from the direction of the car turning. There's no such a force. Your body is just moving in a straight, but the car is moving this way, and the car is running into you. Now you're not being pushed against the wall. Okay? Those are not real forces. Real forces are only these. Okay? I can't emphasize more. Okay? Alright, so these are the forces. What does the Newton's second law say? Newton's second law. This is where the whole fun starts. So Newton's second law says that the net force acting on the object is equal to mass of the object times acceleration of the object. The net force as a vector is equal to mass of the object times acceleration as a vector. Sometimes they say, it is better to say that acceleration is net force divided by m, right? Because it is cause and effect. The net force is the cause, the effect is acceleration. So there's a net force divided by m gives you the acceleration. But because we like to write a linear form of the equation, we say F equals ma. So net force is equal to ma. So what is this net force? Net force means sum of all the forces acting on an object. This is talking about one object with mass m and forces acting on that object. F net as a vector is the vector sum of forces like F1, F2, F3, and so forth. Whatever forces applying to that object, you add them all up as vectors, and that gives you the mass of the object times the acceleration of the object as a vector. Alright, so how do we add vectors? We split them into components. Let me write this in vector notation. F net can be written as sum of Fn, Fi, right? I from 1 to n, if there are n forces acting on the object, and equals to mass of the object times acceleration of the object. But how do we add vectors? When we want to add several vectors, we add their components and they get the component of the total. So adding all the x component of these forces gives you the mass times acceleration in x direction. Because this is a vector, this is a vector. If they are equal, the x component of this has to equal to x component of that, right? And therefore, all the x components add up to m times ax. This is the x component of Newton's law. And then the same for y. And instead of using that vector equation, we use these two components. This is where it becomes complicated because, as I said, people do not distinguish between the vector itself and their magnitudes and their components. So remember, for vectors, we use a name with the arrow on top. When we don't use the arrow, we mean the magnitude. When we have x or y index on them, means the components. If you be careful about those and use them properly, then it becomes very simple. This is Newton's second law. So what we do to apply Newton's second law, usually first we pick one object, because this is talking about one object. This mass is for one object. We pick one object and see what are forces acting on it, what is the acceleration, and then we write these equations for the object. And this gives us two equations, and we can solve for two unknowns. And it allows us to do that. So this mathematical formula for two.